Welcome to the Explainer. Today we're talking about polynomials. And yeah, I know, they might just seem like a bunch of x's and numbers you had to deal with in algebra. But what if I told you they have this secret life, a really deep, elegant structure that's hiding just beneath the surface?
So let's start with kind of a weird question. What could the number 15 possibly have in common with the polynomial x squared minus 4? It sounds random, right? But the answer is where we find this beautiful hidden mathematical structure. Turns out they can both be broken down into these smaller fundamental pieces. Just hang on to that idea because it's going to connect everything we talk about today.
Okay, so check this out. It's a pretty surprising parallel, right? On one hand, you have integers, regular whole numbers. And on the other, you have these polynomials. They seem like totally different beasts. But when you look at their structure, they play by the exact same rules. You can add them, you can multiply them, and, this is the big one, you can factor them, you can break them down. And that last part, that's the key to the whole thing. It's way more powerful than it looks.
All right, before we can uncover their secrets, we got to learn to speak the language. So let's do a quick refresher on the basics, the ground rules of the polynomial world.
So what is a polynomial officially? It's really just an expression you build by adding a bunch of terms together. And each of those terms has a super simple recipe. It's a number, which we call a coefficient, multiplied by x raised to some whole number power. That's it. It's a specific recipe, but man, is it flexible.
So yeah, something just like this. You've definitely seen these before. That's a perfect example. You've got your numbers out front, the 2, the 3, the 7, and you've got your variable x being raised to the powers 0, 1, and 2. See? Simple as that.
Now, every single polynomial has something called a degree, and that's just a fancy word for the highest power of x you can find in it. So for this guy right here, the biggest exponent is that little 3, so its degree is 3. And that piece with the highest power, the whole negative 2x cubed part, that's called the leading term. It's kind of the boss of the polynomial, and it tells you a lot about how it's going to behave.
And just like with our good old integers, you can add and multiply these things. Adding is super easy. You just, combine the terms that have the same power of x. But multiplication is where there's this really neat predictable rule. If you multiply, say, a degree 2 polynomial with a degree 3 one, guess what? The answer is always going to be a degree 5 polynomial. You just add the degrees. Pretty cool, right?
Okay, so we can add and multiply. That's building our analogy with integers. But now we get to the first big leap. This is where it starts to get really, really cool. If we can do all that, then can we also divide them?
I'm sure you remember this from way back when, right? Long division. You take 13, you divide it by 5, and you get 2 with a little bit left over, a remainder of 3. It's one of the first things we learned in arithmetic.
Well, guess what? There's a formal theorem for this, the Euclidean division theorem. And it says you can do the exact same thing with polynomials. If you take one and divide it by another, the theorem guarantees you'll get a unique answer, the quotient, and a unique leftover, the remainder. And here's the crucial part. That remainder will always have a smaller degree than the thing you were dividing by. Always. So with this example, you see it in action. You divide one by the other, and you get a quotient and a remainder. But the main takeaway here isn't just that it's a neat trick. It's that this works at all. The fact that polynomials can be divided so cleanly, that is the key that's going to unlock their entire hidden structure. All right, so we can divide them. Big deal, right? Why does that even matter? Well, this is the payoff. This is where it gets really good because division is the secret bridge that connects finding solutions to an equation and breaking that equation into its parts. You probably remember this from algebra, trying to find the roots or the zeros of an equation. It's that magic number you can plug in for x that makes the whole thing just equals 0. Okay. But look closer. Look at the second half of that definition. This right here, this is the big reveal. It says that finding a root is the exact same thing as saying that x minus that root divides evenly into the whole polynomial. Let that sink in. In other words, they're two sides of the same coin. When you find a root, you haven't just solved a puzzle. You've found a factor. You've found one of the actual building blocks that the polynomial is made of. It's incredible. So for this polynomial here, finding out that x equals -1 and x equals 2 are the roots, that is literally the same discovery as realizing its factors are x plus 1 and x minus 2. They aren't two different ideas. The solutions are the factors. The puzzle and its pieces, they're one and the same. Okay, so this whole idea of factors, this leads us straight to the climax of our big analogy with integers. If polynomials have factors, can we keep breaking them down and breaking them down until we just can't go any further?
Think about it. We know that any number, like 15, can be broken down into a unique set of prime numbers, in this case, 3 times 5. Numbers that can't be factored anymore. It's so fundamental, it's called the fundamental theorem of arithmetic. Well, polynomials have their very own version of this.
Right. So in the polynomial world, we don't call them prime numbers. We have a different name, irreducible. But don't let the fancy word fool you. The concept is exactly the same. These are the fundamental building blocks, the ones you can't break down into any simpler polynomial factors.
Okay, but here's where things get a little mind-bending. Whether a polynomial is prime or not actually depends on what kind of numbers you allow it to play with. Take x squared plus 3. If you're only using real numbers, that's it. It's irreducible. You can't factor it. But the moment you allow yourself to use imaginary and complex numbers, suddenly, poof, it can be broken down. So the rules of the game, they actually change what the fundamental pieces are. Wild. So let's recap. We've got division, we've got prime factors. With those two things in our pocket, we can finally unlock this master tool, one that works for both numbers and polynomials. And it's going to tie this whole analogy together perfectly.
You've probably heard of the greatest common divisor, or GCD. You know, for two numbers like 12 and 18, it's the biggest number that divides into both of them, which is 6. It's a classic idea from arithmetic, and it's just as useful here for finding the largest polynomial that divides into two other polynomials.
And this is the really incredible part. The exact same method, the same step-by-step process we use for integers, the Euclidean algorithm, it works perfectly for polynomials too. You just divide, check the remainder, and then repeat the process with the new numbers. It's this beautiful, universal algorithm that just proves how deep the connection between these two worlds really is. So when you step back and look at it, the really crucial point is that these aren't just abstract formulas. The elegant rules we learned for numbers aren't just stuck in arithmetic class. They create this deep, interconnected structure that reveals a hidden beauty inside of algebra. So we found the rules of numbers hiding in polynomials. And that just makes you wonder, right? What other parts of math are secretly connected, just waiting to be discovered?